Hi, everyone. I'm happy to introduce our speaker today, Majid. Majid is a PhD candidate from University of Toronto. He has done research on human AI interaction, specifically addressing the problem of over-reliance on AI, and also designing user interaction that cognitively engage user in the domain of programming. And he has published multiple papers in top-tier SEI conference like Kai, WIS, and IUI. And I think today he's going to talk about his research. Please take it away.
Wonderful. Thank you. Thanks for the introduction. So yeah, I'm excited to share some of my research that explores, studies, and develops tools that address fundamental challenges surrounding interaction and cognition when using generative AI for programming tasks. Just to give you a little bit of background about myself, throughout my education, I've been an HCI systems researcher, and I had the opportunity to study and research at some of the top schools in the US and Canada, as well as 2 internships at Microsoft Research. I've also had the privilege to collaborate closely with some of the top researchers in academia and industry. So throughout my research, I've been focusing a lot on studying and designing programming support tools, how to make programming more accessible for programmers. And I've looked into the development of tangible approaches to programming to support children in creating their own interactive wearables. After that, I've built intermediary programming environments that scaffold the transition from block-based to text-based programming tools. And most recently, I've been extensively studying the impact of AI on programmers and developing tools to tackle some of its core challenges, which this is going to be the main focus of my talk today. So currently, generative AI is powering a lot of different types of intelligent agents. They can perform diverse productivity tasks using natural language instructions. And for example, using a data analysis agent, we can analyze data, extract insights, and produce reports and visualizations from simple queries. Or using GitHub Spark, an application builder, we can rapidly build web applications, which takes just a natural language description of the application. And rather than displaying any code to the user, it displays the final application that the user can interact with. Or with this fairly new AI agent for conducting a literature review, you can simply provide a topic, and the AI would be able to produce the introduction and related work of a paper on the topic that includes references to published papers. So all of these AI agents are reshaping the way how people are working. They're allowing users to delegate lower-level and repetitive tasks to these AI agents, which in turn enables them to focus on their own higher-level tasks, which require higher-order skills like reasoning or creativity. So this shift has several benefits. It could potentially increase productivity by making tasks faster and easier, and it could also enable more people, including novices, to perform highly specialized tasks. However, this shift in workflow, it's also creating several challenges. First, AI might make mistakes, and verifying the AI's output is difficult. Second, using natural language introduces ambiguity, making the interaction with the AI and controlling it difficult. So these are so far the short-term challenges of using AI. But if we look deeper, we can notice that the low-level processes that the AI is now automating, these have been traditionally processes in which people used to think with, analyze trade-offs, make decisions, solve problems, and even be creative. And with the AI replacing such traditional thinking processes, there is a concern that over-reliance on AI can potentially have negative impacts on independent problem-solving abilities, which I would like to classify as one of the long-term challenges of using AI. So in this talk, in order to address these challenges, I will be focusing on programming as a productivity task that is being significantly transformed with generative AI. So programming languages are powerful types of user interface that drive innovation, automation, connectivity, and creativity. And they're becoming ubiquitous. It is being used in many tools across different industries and by many people without even formal programming education. In fact, prior research has categorized programmers into software engineers or end-user programmers like data scientists or business analysts, and conversational programmers such as UX designers to better communicate ideas. But programming is difficult. It requires skills like abstract thinking and understanding the notional machine, problem-solving skills like task decomposition, as well as following syntax and non-intuitive semantics of code. But generative AI tools like large language models are capable of solving many complex programming tasks simply using the provided specification in natural language. Especially with tools like GitHub Copilot and ChatGPT that are being widely used by a variety of different programmers, from software engineers to end-user programmers for various types of programming tasks. And with more advanced prompting techniques, they can even enable a wider variety of AI agents that can autonomously perform end-to-end complex tasks, such as data analysis. So at a high level, when comparing AI-assisted programming with manual programming, we can see some of the same issues that we identified earlier. Over-reliance on AI in the long term might lead to reduced ability in critically analyzing and engaging with the AI-generated code, lowering programmer skills such as task decomposition and independent problem solving. Additionally, the ambiguities of natural language when using AI can introduce many short-term challenges, such as difficulty in verifying and controlling the AI to achieve a desired solution. So throughout my work, I've been trying to address these challenges by answering the following high-level research questions. First, what is the impact of AI on productivity, over-reliance, and human cognition? How to build AI tools that protect human cognition when using AI? And third, how to enhance verification and control when AI agents are solving tasks autonomously. This brings us to my first project that explores the impact of having access to AI on novice programmers' productivity. But more interestingly, what will happen when AI is removed? Can programmers still independently modify, extend, or write code without AI? Or is there a risk of programmers becoming overly dependent on AI? For that, we conducted a study with 69 novice programmers over 10 sessions, one group with access to an LLM for code generation, and the other group without. The study started with a pre-test evaluation of the participants that evaluated their prior block-based programming skills. Then novices were divided into two groups based on the pre-test scores, and both groups then started to learn Python by working on 45 coding tasks, from the basics of Python to more complex topics like conditionals, loops, and arrays. Each of these 45 tasks included a code authoring part where the AI group had optional access to the AI code generator, but the other group had to solve those tasks manually. And following the authoring tasks, both groups had to modify their solution to the authoring tasks manually without AI. For running the study, I also developed a self-paced programming environment that provided code generation using GPT-3 for the AI group. So in the last phase of the study, we removed AI access from both groups. This is session 9 and 10 of the 3-week study. We wanted to evaluate their independent coding skills without AI. We first did an immediate post test on session 9, and then a week later, we conducted a retention post test that both of them evaluated their code writing, reading, and modification skills. So in terms of results, during the 7 sessions of training with and without AI, the AI group performed significantly better, which is somehow expected. But what is more interesting is that their independent coding skills on the modification tasks after they've had the option to solve the task with the AI. Our results show that participants in the AI group did not perform worse and even performed slightly better. Now, looking at their final evaluation sessions that was conducted a week later to test their independent coding skills without AI, contrary to our expectations, participants in the AI group were performing slightly better on all three types of evaluation tasks, including code authoring, code modification, and multiple choice comprehension tasks. So overall, it seems that the novice programmers that had access to the AI were performing slightly better. But how did this happen? For that, in order to better understand these results, we looked at their pretests. And we performed a post hoc analysis by dividing participants into 4 groups: the top 50% who performed higher on the pretests and the lower 50%. And we expected that the top 50% group to have similar results when they had access to the AI, because these are the top students, the top programmers. But what we found was super interesting. Participants of the top 50% group performed significantly better if they had access to the AI code generator during their training process. However, the lower 50% group, they did not perform worse if they had or did not have access to AI. They performed similarly. So these results so far demonstrate that AI can potentially improve existing coding skills for some participants, for some of the participants. But this was not the case for all. So to better understand the impact of AI on over-reliance, we need to see how and in what ways did participants use the AI. For that, we performed a thematic analysis focusing on the 33 participants in our study that had access to the AI code generator. We specifically looked into their usage patterns with the AI code generator on the authoring tasks. So through our qualitative analysis, we identified 4 different coding approaches. Overall, from the 1,300 tasks that participants worked on during the 7 training sessions, 29% were solved without AI, so completely manually. But then 46 of them were submitted with a single prompt that asked the AI to solve the entire task. So the AI autonomously solved the task for them, of which in 2/3 of the tasks, these programmers prompted the AI by copying the task description, while in the rest, they reworded the task description in their own words. And in the rest of the tasks, participants decomposed the task into several sub-goals. Some only used consecutive AI prompts to solve each separate sub-goal, while to solve 19% of the tasks, participants used both the AI and manual coding for different sub-goals. So this provides an overview of how participants use the AI. Now, what is really interesting is the relationship between using these different approaches and their subsequent modifying tasks. So after each authoring task, just to give you a reminder, after each authoring task, there was a modification task immediately after without AI. And what we found was that the authoring tasks that were completed using the AI single prompt led to the highest authoring score. But this was dropped by 30% in the subsequent modifying task. A similar effect was seen for the AI step-by-step coding approach with a 20% drop. But the hybrid coding approach resulted in the highest average of both authoring and modification performance. And interestingly, not using the AI for the authoring tasks resulted in a 10% increase in the subsequent modification task scores. So what we can see here is that at a high level, using the AI to solve the task, solve the entire task autonomously led to the highest performance on the code authoring parts. But it also led to the highest drop of performance when AI was taken away for the modification part. We also saw similar results with their retention post-tests that was conducted a week later. In other words, using AI consecutively for to solve the entire task autonomously for these programmers reduced their independent coding skills. But how can we prevent this drop of performance? Or in other words, how can we protect human cognition when using AI? Which brings us to my second project, where I look into a design. Well, I took a design-focused approach to design interfaces and interventions that engage programmers in AI-generated solutions as a way to prevent skill degradation. So current AI tools, they display AI-generated code to the programmer and usually include some explanation about how the code works. However, engaging with the code or the provided explanation is completely optional. But what if we add a little bit of forced engagement with the AI-generated code so that without being disruptive or annoying, it could properly engage the programmer in the generated code, bridging their knowledge gaps effectively and help them apply concepts from the AI-generated code to similar tasks without AI? We had two important design considerations in our design exploration. A good technique should maximize and effectively support programmers in understanding the AI-generated code so that they could write or extend code of similar complexity without AI. And it should also not increase cognitive load and frustration, which we're calling friction in this work. So to systematically explore the design space, we designed and developed 8 different cognitive engagement techniques, each using different ideas to engage the programmer in the AI-generated code. Now I will show you 3 of these techniques. First, explain before usage, in which the AI-generated code is displayed to the user, but before the user can use the code in their editor, the AI is going to ask the user several questions about the code and forces the programmer to think about those parts of the code and answer those questions before they can use it in their editor. So this is a video of it. These are like they could ask, the system asks short answer questions or multiple choice questions, and users will receive feedback on their input and can have multiple attempts. And once they're done, they can click on return to editor, and then they can use the code in their editor. The second technique that I want to talk about is the trace and predict. It displays the AI-generated code to the user, but again, before they could use it in their editor, it requires the user to trace the code line by line. And at several lines, the system pauses, and it asks the user to predict what the value of a certain variable will be after that line of code is executed. So for example, here, the user is asked to predict the value of the stack after the line is executed. And so after that, the system also asks questions like, why is something initialized to a particular value? And they can engage in an interactive discussion with the AI and then continue with tracing the code until they finish tracing the entire code. And once they finish, they can return to the editor. And lastly, the lead and reveal technique, in which the AI does not display the full solution and instead engages the programmer in thinking about what needs to be done at each line of the code. Once they correctly predict the required behavior of that line, the AI then reveals the corresponding code to that part. So this process will continue with every line until every line of the code is then revealed to the user. For example, here, it asks what data structure should be used. And once the user gets it right, it reveals that line of the code. And this process is repeated with every step. And then once they answer correctly about that step, it reveals the code for that part. And once they have the full code, they can use it in their editor. So just to reiterate, we wanted to make sure that the technique that we wanted to, the most effective technique should maximize understanding and reduce friction. So in order to find the best technique, the most effective technique, we performed an iterative design process with 124 programmers in 2 studies. We first did a participatory design session with 4 programming educators, and then we conducted a between-subject study with 82 programmers using the 7 techniques that we developed and the baseline technique, which did not impose any forced engagement on the users. This showed us how all of the techniques improved independent coding skills, either manual coding or coding comprehension skills, compared to the baseline, which you can see in the green one. So it was basically helping us to show that these cognitive engagement techniques were effective in increasing their ability in independent coding skills. And what we did was that we identified it helped us identify the top 2 techniques and refine them based on feedback that we received from users. The trace and predict and the lead and reveal techniques were the top 2. Lastly, we ran a within subject study with 42 novice programmers using the top 2 techniques and the baseline with no forced engagement. And I would like to go into detail about this particular study. So in this study, we recruited 42 novice programmers carefully so that they all have the same level of programming expertise. And we wanted to make sure that they're working on programming tasks that were designed to be slightly outside of their skill level, outside of their comfort zone, or in learning sciences, we say outside of their zone of proximal development. And that was to justify that they would need the help of the AI to solve those tasks and eventually learn from those tasks and be able to work on those on similar tasks afterwards without AI. And that's exactly what we did. In the first phase of the study, participants used the final 2 cognitive engagement techniques and the baseline to work on 3 topics of programming tasks. And for each task, they first had to ask the AI to solve it for them, and then immediately the AI would then assign one of the techniques to the users, and let's say the lead and reveal or trace and predict, as a way to engage with the AI-generated solution. And after they were done working with the cognitive engagement techniques, they were immediately asked about their perceived ability to write or extend code of similar complexity. So we basically asked them how confident you are in writing code of similar complexity without AI on a scale of 1 to 7. And after participants used the 3 systems, in the second phase of the study, we evaluated their actual ability to write or extend code of similar complexity. And we asked them to work on 3 pairs of coding tasks based on the 3 topics that was used in the first phase of the study without using any AI. This enabled us to measure how each of the techniques impacted participants' ability to correctly assess their own performance without AI. So now, in terms of results, we did not find any meaningful differences in their ability to write or extend code without AI. They all performed similarly. But in terms of how each of the techniques impacted participants' ability in correctly predicting their own ability to solve similar tasks without AI, we looked into how their perceived ability and actual ability correlated. And what we found was that using the lead and reveal technique, which guided the users into the step-by-step process of how this AI is solving the task, and they had to predict what the AI needs to do in those steps, it significantly increased programmers' ability to evaluate their own performance, which could potentially also lead to more optimal engagement. Now, in terms of the amount of friction that the systems introduced, we looked into their task load when using the techniques, the completion time, and their accuracy of performance during their engagement. What we found was that the trace and predict system created the highest task load for the programmers, while the lead and reveal did not introduce more task load compared to the baseline. In terms of completion time, using trace and predict took almost 3 times more than the baseline, while the lead and reveal took about 2 times more than the baseline. And when using the techniques to engage with the AI-generated code, participants performed significantly better with the trace and predict. And this is showing that when they were using the lead and predict, they were much more challenged during their engagement. Overall, the lead and reveal system was the most balanced system. It improved participants' alignment between perceived and actual ability, and it did not increase their perceived task load, despite it took around despite it took longer for them to complete the tasks compared to the baseline system. This shows that engaging the user in the step-by-step process of how the AI is solving the task can potentially be a solution to protect human cognition without creating too much friction. Okay, so all the things that we've seen so far in this talk were using the AI to solve very simple tasks in which most AI tools are capable of doing very well. But what if the AI makes mistakes, which is probably true for more complex tasks? And then how do users verify the AI's output? How do users control and fix if the AI makes any mistakes? So this brings us to my last project: how to improve verification and control when AI agents autonomously solve more complex tasks. So LLMs are able to solve complex tasks like data analysis fully autonomously. They can have, by having access to a summary of the data set and a task description. The LLM first generates its reasoning for solving the task, and then it generates a code for it. And then it will be sent to a code interpreter agent for code execution and then displaying the results. This is done with chain of thought and React prompting techniques that have become widely popular. But then currently, the most common interaction method with such AI agents is a turn-based conversational user interface, in which the user has to write follow-up queries to steer the AI if they are not satisfied with the output. Now let's see a quick example of such conversational interaction. Let's say we have this data set of anime series, and we are interested in their themes and tags of these different animes. And we particularly want to know what is the most common tag associated with each theme. For that, we can use a tool like ChatGPT data analysis, which allows us to upload the data set and write the data analysis query. Since the AI does not know about the structure and contents of the data set, its reasoning process, the AI's reasoning process, makes it generate a code that displays the summary of the data set. Then the code execution agent will run the code, and the output is then fed back to the AI to determine how it's going to solve the task. The LLM will look at the data set and then will generate a code to solve the user's task, and then the code is executed, and the final result is displayed. However, if we look deeply and carefully, we can see that there is a problem. Some themes and tags start with an uppercase and some with a lowercase. This is a problem that we need to fix. So here, instead of telling the AI how to fix it, I'm just going to tell it that it seems that there is both military and military with different casings, and I just want it to handle it for me. The AI then uses this new assumption to retry solving the task, but this time after making every tag and theme lowercase. So you can see how this can become more and more challenging as the errors become more subtle, which is actually the case in many data analysis scenarios. So to better understand the challenges that users encounter with when doing data analysis with a conversational AI tool, we conducted a formative study with 15 data analysts. We assigned them with several data analysis tasks and data sets, and we asked them to use ChatGPT with the data analysis plugin that was available in 2023 to solve those tasks. We then asked participants to think aloud during the study. So by analyzing the participants' think aloud and usage of the AI tool, we found out that first, participants were overwhelmed by the long responses and conversation history that was generated by the AI. So to help users focus on smaller information chunks at each time, our first design goal was to prevent the AI from autonomously solving the entire task, and instead using multiple intervention points and progressively revealing those responses as it solves the task. The second challenge that we observed was that participants spent a lot of time understanding why the AI has generated a code. They meticulously looked and inspected the code and wanted to understand what were the AI's assumptions behind that code, behind generating that code. To address this, our second design goal was for the AI to explicitly generate and display its assumptions right next to the code that was generated. And then we wanted those assumptions to be displayed using editable UI components at each intervention point to allow users to fix them if they were not what they wanted. And the third challenge that participants had was that they heavily asked follow-up queries inside the main thread of the conversational user interface that were unrelated to the main task. What they did was that they asked data exploration, code explanation, and output verification queries right inside the main thread of the conversational user interface. So to address this, and what I wanted to say was that, and this cluttered their conversation history a lot. And to address this, our third design goal was helped assisting users in running side queries at each intervention point that would help them perform these side operations, these data explorations and verifications without cluttering the main conversation thread. So to build a system that would actually address these design goals, the AI should decompose the task. But how should it decompose the task? How many intervention points should the AI create, and at what levels? How much information to display at each intervention point? And how structured should the displayed information and editable assumptions be? So based on prior research and our own experience using and building AI-powered tools, we designed two new systems. The phase-wise system that decomposes the task into different abstraction levels from high to low, while the stepwise system decomposes the task into a sequence of sub-goals of the task until it's finished. Both systems start with a simple input query and data set. The system then automatically creates a comprehensive summary of the data set for the LLM as textual information about each column. So now let's talk about the phase-wise system. It decomposes the task into three abstraction phases: input and output assumptions, execution plan, and code and output. First, the AI retrieves all the relevant columns in the data set, and then it displays all the assumptions that it's able to make about those columns that are related to the task. And then here, everything is editable in a structured way, including the assumptions themselves, the columns, which users can add or remove relevant columns to the task, and then users can also inspect each column for more details, including descriptive stats. And then once they're fine with this input and output assumptions, and they're satisfied with everything, they can move on to generate the next phase. In the second phase, they can see how the AI is going to solve the task using an execution plan, which is a natural language plan of what the AI wants to do. Users can edit, move, and select from optional steps in the execution plan. And once they're done with this phase and satisfied with the state of things, they can move on to the next phase, which is the code that is going to be generated based on the execution plan. And the code is editable. If the user is not satisfied with the answer so far, they can either either edit the code directly with the AI or go back and edit previous steps, which would then require regenerating the preceding steps. Now let's look into the stepwise system. The task in the stepwise system is decomposed into multiple subgoals. It solves the problem one step at a time until the task is finished. Each step has two components: assumptions and actions in natural language, as well as corresponding code and output. At first, it simply reads the data set, and the user can inspect the intermediary variables of the data set. And then it would generate the initial set of assumptions for the second subgoal. These assumptions are formatted in a way to show the assumptions and the corresponding action in natural language, allowing users to edit them directly. And when they're happy with the assumptions, the AI then generates the next step. They can move on and with generating the next step, the corresponding code and its output. So this process will continue until every step of the task is done and the task requirements are satisfied. We also developed two features to allow users to perform side operations during the data analysis process. In both systems, users can also run side queries to perform data exploration on the side without derailing from their main conversation thread. So these side queries are in natural language, like draw a histogram or show me all the unique values in this data frame. And they're executed and displayed on the side of the user interface. They can also select parts of the code to either ask for an explanation or directly modify the code using a natural language prompt. So to evaluate the effectiveness of our system compared to a baseline, we also developed a conversational user interface as our baseline system. It was basically a chat GPT that also that had no intervention points, and asking follow-up queries was the only method of steering the AI. The system also displayed its assumptions in natural language that were not editable. For evaluation, we ran a within-subject study with 18 participants in which they worked on 6 data analysis tasks. So the interesting thing about this study was that we designed these tasks in a way that the AI would actually produce incorrect responses if the user did not involve with the process. And we basically injected 2 issues and 2 problems in each of these tasks. And the users had to verify the output and steer it during the process, making sure that they would find and fix those 2 injected problems. So in terms of results, in terms of performance results, like verification accuracy and time on task, as well as the task success rate, all 3 systems performed similarly. But in terms of perceived ability, that was measured through these Likert scale questions after using each of the systems. Both stepwise and phase-wise were perceived to be significantly better in terms of how easy it was to verify the AI's output, how easy it was to intervene and fix whenever it was making a mistake, and then their own sense of control and confidence over the AI's process. So now let's look into the editable assumptions. Almost all participants appreciated the ability to directly edit the AI's assumptions and to align the system's operations with their own expectations. This is a quote that I really love from our study, where a participant says, "I could add any assumptions that I had in my mind and make it the AI's assumptions." Another dimension, so in terms of when we look at the assumptions from the spectrum of being editable to non-editable, and a very interesting thing that we found was that when the assumptions were editable in the phase-wise or stepwise systems, users tended to be more critical towards the assumptions. But then when the assumptions were displayed but not editable, like the baseline system, users tended to accept them without even questioning them. And it was also a source of frustration and lack of control. Another dimension that we looked into was how structured the information was displayed in different systems. So the phase-wise system is a system that has a lot of structure, and users found that they could have these finer controls over the AI, and it helped them find information easier, but it was also a source of information overload. However, with less structure, like the stepwise system that only displayed the assumptions of the next step, they found that it's very difficult for them to make targeted edits. Additionally, the smaller steps of the process used in the stepwise system, it improved participants' confidence, as they were not scared of making new edits, and they thought about every step they thought about verifying the AI's output at each step along the way. And it also felt more similar to how they would approach their own data analysis process. which was an important benefit of the stepwise system. But interestingly, there were several participants that liked the baseline, the conversational user interface for some situations. Particularly, they were less critical about their own edits, which were basically the follow-up queries, and they liked that the AI is producing feedback much faster, and it also had a much easier to understand mental model of what the AI is going to produce. So while both systems were preferred over the conversational baseline, both the phase-wise and stepwise systems, the stepwise system seemed to be the most balanced system. It improved confidence and users' sense of control over the AI's process. It helped with verification through a step-by-step way, and it did not cause information overload. So now let's take a step back. What are we understanding from all these projects? At a high level, it seems that when AI agents are solving a task fully autonomously, it is the source of those challenges that I mentioned earlier at the beginning of the talk. The short-term challenges of verification and controlling the AI, as well as long-term challenges of reducing independent problem solving and negative impacts on human cognition. And interestingly, we can see that our results and design explorations are pointing to a single solution that could potentially solve both of these challenges. By preventing the AI from autonomously solving the tasks and instead involving the user in how it's solving the task, it allows users to understand the AI's assumptions throughout the process, check those assumptions, and if needed, to correct the AI. And this would potentially improve short-term productivity gains while also preventing long-term skill degradation as the user is involved and is in how the AI is decomposing the task and solving it. But an important question that I would like to bring up is that does this mean that we do not want AI agents to autonomously solve tasks? Is involving the user in the AI's process always the better way of going? So my personal answer to this is no. I believe that. That it depends on the amount of complexity of the assumptions that the AI is making when it's solving the tasks, especially those assumptions that are unspecified by the user, such as when they're writing the original prompt. And therefore, the AI has to guess them and come up with the best assumption for those. These assumptions are used by the AI to make the decisions for solving different parts of the tasks. They are difficult to understand, they're difficult to check and verify, and even difficult to update. I think this is what we need to solve for the future of human-AI interaction, to either reduce the number of unspecified assumptions that the AI is making by improving input prompts or making users to reduce the number of unspecified assumptions that the AI is making, or make the users engaged in those assumptions and allow them to be aware of them, understand them. Let the AI report its own confidence about those assumptions and involve the users in correcting them. So in terms of future work, at a high level, building on top of the recent work that I've been doing in terms of exploring and addressing some of the challenges of human-AI interaction, the next step seems to be taking a deeper look at the different parts of our interaction with AI agents. How to design future AI interfaces for complex tasks that actually enhance user productivity. Specifically, how to provide input to AI, how the AI involves the user in its process of solving the task, and then how do users engage and use the AI's output. To reduce unspecified assumptions during the prompt writing process, one method is to combine direct manipulation interfaces with natural language interfaces. And so one idea is to enable users to refer to existing elements in the context, refer to the capabilities of the system, or even refer to abstract ideas and vocabulary about the topic. And using these references, the AI will have access to a much more well-specified prompt and eventually make less guesses and assumptions during the process of solving the task. Another method to improve quality of task specifications during the prompting process is to support users in the task decomposition process. So how can we develop interfaces that help the user think more deeply about the task that they're working on and let them break it down as it's into like these actionable and concrete items as if they were delegating it to someone else? How can the system then provide immediate feedback during this prompt writing process, help users provide more details for abstract ideas that they're writing inside their prompt using natural language? And then many tasks that we want to solve are exploratory in nature, but current AI tools do not provide the required interaction paradigms to help users in those exploratory processes. What if AI tools could display their important decision points, the divergent thinking and convergent thinking processes, and help us explore all the different assumptions that could be, well, not all the different, but the most important assumptions that could be made at each of those steps, and then display its own confidence on those assumptions, helping the user through the exploratory process. And from completely different perspective, what if the user is basically asking an incorrect question? What if the user has an incorrect mental model about the task that they're working on? And how should the AI respond in those scenarios, make the user reflect on their prompts and improve their mental models, and then respond based on the reflection of those mental models? So how can we make the AI to be less obedient and instead challenge the user through the process of solving tasks? And then in terms of the AI's output, once the AI has produced the final output, how can users debug the final output, see the assumptions that were made, and then go back and select from different assumptions to see different variations of the output as a way to get to the most satisfying answer? Another line of research that I'm also interested in is about the future applications of AI agents, specifically for the future of research. So currently, there are many tools that are being developed to make reading more accessible. However, they may unintentionally reduce critical engagement with such AI enhancements about how we read a document. They might overly simplify details and limit deep synthesis of ideas. So here I would like to build on my previous research in cognitive engagement with AI and build interfaces and tools that would ensure that users are critically analyzing the parts that the AI is focusing on and help them make better engagement with the document. And then an important part of research is developing prototypes. However, most AI tools currently are using are doing the prototyping process in a complete autonomous way. They do the task from an end-to-end in an end-to-end way without any user involvement. So how could we improve this process? How can we create tools for prototyping in research that would help users verify the process throughout verify the AI's process? And then lastly, when we use AI to perform writing tasks, how can we ensure that the AI's output is actually what we want? How do we know if the AI has not missed some of the things that we wanted? And how to be involved in the assumptions that the AI is making throughout the process of generating content. Thank you for listening, and with that, I would be happy to take any questions.
All right, thank you for the talk, Majid. Now we have some time for questions.
I have so many questions.
Okay, Sergi, start.
Hi, I'll ask one. Thanks for the interesting talk. I use AI assistants all the time for coding, so this is personally relevant to maybe all of us. I have a question about the LLM's ability to produce assumptions that are actually related to the code that they're going to write. So I guess I have my doubts that the assumptions they would produce would be A, faithful, B, complete, or C, that if you edit them, the code would be edited also in a faithful fashion. Do you see evidence that modern large language models can actually do this? And if not, do you think we can train them to do that?
That's a great question. You have part of your answer in the question as well. So yeah, I'm not seeing like GPT-4o or even O1 or what is the other one? The reasoning model.
O1, yeah.
Yeah, to be making very, very well assumptions. I think that's a very important problem, and they're not doing well. And I haven't tried models like DeepSeek, but as you mentioned, I think one of the ways to move forward is to actually train models to have to have the model like include maybe a tree of thought or something like that within the training process, for it to not just be like this is input, that's output, but also like the tree of thought. But yeah, I think that's an open problem. I have not been able to get very reliable results. However, in data analysis, I created some like prompts that we're fine. We're much better. So eventually, I am actually using for my own data analysis processes. I'm using the tool that I've built. I'm no longer like ChatGPT or even Jupyter Notebooks. I feel like the tool that I've built was pretty good for that. So I think it really depends on different situations. Like data sets and data analysis tasks, it might work well.
Thanks.
Can I ask a follow-up question to that? So you said like, what is the difference between the data analysis task and programming task that making an assumption in one is easier than another? The first question. Second question is for if you have a research assistant that help research scientists doing, say, literature review, what would that like? Would similar set of attributes of those domain be applied to this as well?
Sorry, could you repeat your second question?
Okay, just the first question is what is the difference between programming and data analysis that making an assumption in one easier?
So I think the main interesting thing in data analysis is that it's very like the context of the task is there. We've got a data, and then there is a way to explain that data to an LLM. How? By like creating this, I don't know, JSON or whatever that describes the description or the contents of each column, right? Mm-hmm. Let's say you have that. The LLM is actually able to make really good assumptions about that. It's basically what I'm saying is that we're providing a lot of the context to the AI, and the AI is able to like have access to that context. And then since it has other domain knowledge, like let's say the data set is about, I don't know, some fire somewhere. It might know some assumptions and like have some like domain knowledge and expertise about like data sets about fire. I don't know. It might have been trained on Kaggle and these types of things. So the problem with programming tasks, however, is that back to like the data analysis, I feel like sometimes the queries that we have in data analysis are actually those natural language, very simple queries that we want, like what are some of the insights? Like we basically ask a question to get some insights. But in programming, that's not the case. Like usually a different process, at least that's like, but it really depends on what the user's program. If it's a React web application, then first of all, the code is going to be huge, like the output. So I think there are very different contexts. Your second question was about like literature review or something.
Yeah, I think I also want to make sure that we can come back to this later. I also want to make sure that other people have time to ask questions as well.
I guess I could go. Hey, Manjeet, Joseph here. So I have a question about your work on stepwise versus phase-wise design. I guess at the conclusion, you sort of settle on stepwise being the more balanced and preferred method from your study. I was wondering if you see the phase-wise design still being useful in some other domain or some other scenario, or do you think that the conclusion is very generalizable?
So first of all, we did not get statistically significant differences on our study in terms of like how well one group with one system was able, with one system participants were able to like verify things better. We did not get that. But users loved that they can like have these user interface direct manipulation type of edits here on each column of the data set. This was something that was only in the phase-wise system, but not in the stepwise system. So the stepwise system only displayed the assumptions, and it was like very generic. But here, yeah, I think they really loved this as a way to like control every single column.
So then basically being able to see all the details and everything being very transparent was the biggest factor then?
I think it kind of boils down into like showing the right information in the right time. And this, in many cases, was the right information at the right time. They were able to like see some of the assumptions that the AI was making that was wrong or was not making it and it was missing, and that helped them fix it. But in many cases, it was just a lot of information, and like they were just bombarded with it, and they didn't like it. So I think it requires a balance, and maybe sometimes just like the AI like proactively maybe showing, like retrieving a relevant column might be a good solution in some case. Maybe a combination would be good, like a stepwise system that displays the like something like a column here that you could like refer to a column and the assumptions about that column.
Got it. Thanks.
One more minute. If people want to ask a question.
I guess I could ask one last question. In the future work part, where you talked about combining direct manipulation and natural language interface, which I thought was very interesting that you talked about referring to specific elements, referring to specific capability. Well, one thing that you mentioned was referring to abstract ideas. I didn't quite understand what you mean there.
So I think what I'm trying to say here is that sometimes people don't even have the vocabulary to describe something. And that is something that we have not been thinking in human AI interaction. So what are I think that it's a bit different than the capabilities of the system. It's about how we think about the problem and how we try to describe it, and then make it more concrete, make it more well specified.
So kind of like user-defined concept, maybe?
User-defined what?
Like a user-defined concept.
Or yeah. So as they're writing a prompt, they might be like thinking about an abstract idea, but how can they like make it more concrete?
I see. That makes sense. Thanks.
Okay. All right. Thank you very much, Majid. And I think that's pretty much wrapping the talk for today. The recruiting team will be in contact once we have decision on the next step.
Sounds great. Well, thanks again for listening, and it was great seeing you all online.
All right. Thank you.
Thank you.
Have a good one.
Have a good afternoon. Bye.